Hello and welcome to another Zosin session. How about that? So I've been developing this linear algebra library recently, which you can find in the description, of course. It's currently at the state where I'm more or less happy with the library, except I think it lacks some examples on how to use it. Right, so, and today what I want you to do, I want you to write a small demo that sort of shows how you're supposed to use the library and what you can do with the library. It's a very simple library. It doesn't really need anything complicated. But I want you to implement something fun, right? So something fun. So I have an idea of implementing like a simple animation of like a bouncing ball, which simulates like a very simple physics like gravity and so on and so forth. And to keep the amount of dependency low, I was thinking that I'm going to render the ball in ASCII in the terminal, right? So it's going to be a very simple program that renders, animation in ASCII and just animates the bouncing ball. And we're going to be using vectors for that, and the vectors are going to be from this linear algebra library. So we actually started to develop this thing like 3 episodes ago. I think this is the 4th episode. So for a playlist of all of the episodes of this like library development, I would redirect you to Tsoding Daily channel, which has playlist, I suppose. So as of recording, the 3rd episode is not out yet, right? I think. Yeah, so as you can see, it's privated, so it's not out yet, but it's gonna be out when this video is out already. So I'm gonna put the playlist in here. Playlist of the previous episodes. There we go. The previous episodes. Let's capitalize everything nicely. All right, let's go ahead and implement that thing. So, and we're gonna put this demo into the source code of the main repo, so you'll be able to download the source code and also take a look at the examples and see how you're supposed to use this kind of thing. All right. So let's create a file called ball.c. And the first thing we're gonna include the stdio for the input-output, of course. Let's create an entry point. It's not going to be doing anything. We're not going to accept any arguments. User have nothing to say to us. And let's define LA implementation, because this is a header only library. And let's include that library. Okay, so let's include the compilation of the ball example into the make file. Right, so what we're doing here, we're building the library itself, and we're also going to be building a ball. Right, and ball depends on ball.c and the library itself. So if we modify the library, the ball has to be rebuilt as well. Right, so what we're going to be using C compiler, the common C flags. The standard that we're going to be playing with is C11. So the library itself tries to keep it C99 just to make it more like widely integratable. I guess that's the word. But for our example, we don't have to follow that, right? It's just an example, it just demonstrates how we use the library. All right, so, and let's just compile the entire thing. I didn't think we need to link with the math library because we're not going to be using any math library features. So, and let's go ahead and rebuild the entire thing. And as you can see, we managed to build this thing. All right, so that's already pretty good. So we're going to be rendering everything in ASCII, and because of that, we probably need to define the width and height of the display that we're going to have. We're going to have like basically an array of characters as the display. So let's define width. So you don't really need too many characters in the terminal. Terminals are usually very small. So let's actually say that width is going to be 32 characters and height is also going to be 32 characters. I'm going to keep it powers of 2 because it will make it easier to divide it by 2. Because it's a power of 2. Okay, let's define the display, and the display is going to be an array of characters, width by height. And let's keep this thing static, so it will be 0 initialized for us. All right, so we need some sort of a function that will render a circle in the display. right? Let's implement a function literally called circle, right? It will accept the center of the circle as a two-dimensional vector of integers, right? So this is the center of the circle, and it will accept an integer, the radius of the circle, right? And so what will this thing do? It will render the circle at that specific center with that specific radius within the display. Right, so we're going to be rendering this the circle pixel by pixel, and I think we're going to employ the midpoint circle visualization algorithm that we developed in one of the previous videos. So let's actually go to the Coding Daily channel. Coding Daily. So the video is called Programming in Rust. So in this video, I actually went to one of my previous projects, and one of my previous projects was actually looking into the midpoint visualization algorithm. Right, so let's take a look at it. Here it is. And there we re-implemented it and generated a circle pixel by pixel like so. Right, so here's the final thing. I'm trying to right click this and I think it doesn't allow me to do that because Chromium do be like that sometimes. So to fix the Chromium, I have to open another application that supports right clicks, right? Then I have to do right click, right? And only then I can right click in the Chromium yet again. I have no idea if that's the bug of Chromium or my environment or something like that, but it do be like that sometimes. Okay, so and yeah, here basically we generate a circle completely from scratch, pixel by pixel, just using mathematical formulas and stuff like that. And this is basically the algorithm that we're going to be using to do the ASCII graphic, right? So basically, character is just like pixel, right? Just big pixel. It's just bigger. So yeah, I'm gonna give the link to this video in the description. So where is the description? So midpoint visualization algorithm. And by the way, we did that in Rust. So if you guys like Rust, you may like this video, right? Because we were programming in Rust. So I'm also going to mention that in Rust video, right? And you can find it in here, and in the description on that video, you can find a lot of interesting links and link to the repo itself, and so on and so forth. So I left a lot of interesting things for you to explore. Okay, so we're going to be using that algorithm. Let's go back here and let's see what we're going to have in here. So essentially, let's imagine that we have some sort of a display, like something like this, right? And then we were told that we want to render a circle somewhere here, right? So this is where we need to render it. Essentially, we need to find like a bounding box that encloses the circle. We know the radius, right? So if we step up the radius and then right the radius, we'll find the left top corner of the of this bounding box. We can repeat the same thing in the other direction, right? So this is going to be 1, 2, 3, 1, 2, 3, and there we go. Here is another thing, and there we go. We found the bounding box, right? So we found the bounding box, and now we can take that bounding box and we can iterate it with a nested loop. Right, we can just iterate it with a nested loop. I just really want to finish because my OCD doesn't allow me to not finish this entire session of replacing characters. Yeah, there we go. So there we go. So distance between the center and this side is radius, and distance between this one is also radius. So we're going to be iterating each individual pixel like this, and then with a simple formula of x squared plus y squared less or equal radius squared, we're going to check if a particular point within that bounding box lies within the circle, and if it is, we're going to be setting it to something, right? We're going to be setting it to color, but in our case it's going to be character, right? So, and that way we're going to essentially fill in everything. So maybe I'm going to put like this here, right? And maybe it's going to be like that. I don't even know how it's going to look like, but I would imagine that the final result will probably look like this, if I would imagine, right? Because it kind of makes sense to me. Yes, roughly. Cool. So let's go ahead and do that. So let's actually find the, you know, left top corner. So to do that, we'll have to take the center, right, and we'll have to subtract, I suppose, the radius from the center. Radius as a scalar, we'll have to convert the radius to a vector to be able to actually subtract this entire thing. So vector 2i, if you take a look at the implementation of this function, right, it just takes a single argument and basically splits it into like two components of the vector, right? So essentially v2i 2 is basically v2i 2, right? So you can clearly see that. So if you're interested in any of these functions, how they work, you can easily find them within the source code of the library, and they're pretty straightforward. They're very simple. You will see how they work. There's no magic in here. So we're subtracting the radius, and this is essentially our beginning, right? So this is the beginning. And now we need to do the end. And for the end, we're going to be adding the radius to this thing. Interestingly enough, right, if the radius is 3 and you add 3, you cannot go outside of the circle, right? You cannot go outside. You see 1, 2, 3, but if you add 3 to here, you're going to be going in here and you're going to be checking the... I don't know what my neighbors are doing, but anyway. So you're going to be checking extra characters that's not going to be part of the circle, right? But maybe it's not going to hurt, right? So maybe it doesn't matter because they're not going to be part of the circle anyway. So I guess that's fine. What I was thinking about, maybe we could just do something like -1, but I don't think it matters, right? So at the end of the day, they're not going to be included in the circle. So, and what we're going to be doing, we're going to be iterating through each individual pixel of this square, right? So we're going to start iterating row by row. So we're going to have y, it's going to start at the beginning of y, and then up until the end y plus y. Okay, begin end. The same thing goes for x. So beginning x less or equal end x plus x. Cool. So and if square x plus y square less or equal than the radius square, we have to place some sort of a character into the display, right? So we need to do something like this: y multiplied by width plus x, and it has to be equal to, let's say, star, right? Let's put star in there. Otherwise, we're not going to be doing anything. So that probably also means that we have to fill the display with some sort of default color. And maybe to do that, we're going to have a special function fill, which accepts the pixel, and it's going to fill the entire display with that specific pixel. We can use memset for that. We can just take the display, because even though it's square, it's still continuous in memory. So we just store everything row-wise. So that means we can take this entire thing and set it to one character like at once without, iterating anything. Right, we're going to set it to p, and this is going to be basically width multiplied by height. There we go. So this is how we're going to be filling everything. Okay, so does this stuff even compile? Does this stuff even compile? I think I'm going to actually keep this comment somewhere here. Maybe I want to actually do it like this. So this is the center, right? Then this is the center. And this is the radius. So I'm not really sure if that's a good idea to make it so. Yeah, it was a good idea because I already used r here as the radius, so it would fail to compile. But I mean, there's nothing wrong with compilation errors. Compilation errors are designed to actually help you catch bugs in your code before executing the code. All right, let's try to compile the entire thing and see what kind of compilation errors do we have. So we don't have a memset. As far as I know, memset is defined somewhere in string. Let's define string. And we don't have v2a add. Oh, it's called sum. Yeah, I do remember that it's called sum. Maybe we could add like an alias for v2 add, because I keep like confusing add and sum. So yeah, let me actually put it to do for that. v2 star add alias to v2 sum cos I keep confusing them. It would be nice to have something like that, but not for now. Not for now. All right, so we can fill the entire display with, let's say, spaces. And then let's try to draw a circle. Let's draw it in the left top corner somewhere, right? So it's going to be v2ii, this is going to be 0, and the radius is going to be, maybe it could be like a half of the width, right? So let's actually use half of the width to render this entire thing. And another interesting thing, I just realized that the x and y could be out of bounds, right? They could be out of bounds. So it probably would make sense to first check if x and y was that, and and if 0 less or equal x and x is less than width, and 0 less or equal y and y is less than height, only then we can be placing that pixel into the display, right? So that's basically what we're going to have in here. So after we filled everything with space and rendered the circle, I think it would make sense to display the display, you know. So let's implement some sort of function like show, right? Whatever. Void show void, right? And this entire thing is supposed to just print the current state of the display, right? So you can fill the display with some sort of a color, you can render a particular thing, and then you can just show that display. Should be pretty straightforward. So how are we going to be doing all that? We can just iterate and print character by character, but it's not particularly efficient. I would like to actually print it row by row to reduce the amount of write calls, right? So because the more you sort of bundle up the write calls, the faster usually program goes. But I think it doesn't really matter in C, because in C by default, like specifically in my environment, the output is buffered anyway, so maybe it doesn't matter, but I can just do that just in case. Why not? Let's actually iterate row by row. Right, so this is going to be height. And then what we're going to do, we need to take the next row. So the next row is located in here, so this is going to be width. And let's use function fWrite. Man fWrite. Okay. So this is going to be that. Let's copy paste this entire thing. The thing we want to write in here is display. So next we need to say the size of the element that we're writing. Let's say that the single element we're writing is the single row. So the size of the element is going to be width. And the amount of elements is going to be 1. We're rendering one specific element, which is the row, and we're printing it to stdout, right? So we're just going to print it to stdout, and that is basically it. So after that, we can probably print the new line to the stdout as well, and there we go. We print it like line by line. So sounds good. Let's try to compile the entire thing, and something does not really work. Well, fWrite make pointer. Oh, I have to take the pointer of this thing. There we go. Now we're talking. So we have everything, and let's see if it's going to produce some sort of the circle. I think it did. It kind of did. So that's pretty cool. I suppose it's like a quarter of the circle, because the center of the circle is at the left top corner. So one of the things we can try to do, we can try to construct the center like so. We can take width, height, and we can essentially divide this entire thing by 2, right? We can divide this entire thing by 2, and that's going to be our center, right? I can even do something like center, v2i is center, and just reassign this entire thing like that. And maybe I should actually rebuild every time I run the entire thing, and nothing happened. Literally nothing happened. I wonder why. I wonder why nothing happened. Did I forget to do something super important? I think I did in fact forget to do something important, because what I have to do here, I have to do the distance between those things. Yes, okay. Oh boy, right. So what I have to do is just dx, and it's going to be cx minus x, and this is going to be dy, and this is going to be dy. So this has to be dx. So because we're computing the distance. All right, so I already see what kind of mistakes I did, and there we go. Now everything is perfectly centered. Oh, we have a classical problem in here of the subpixel errors, right? So yeah, this problem was discussed in the previous video about the midpoint visualization algorithm, and essentially the problem is because so I'll just wait for my paint. So if we take a look at the pixels, right? So here are the pixels. You can treat, for all means and purposes, the pixels in this particular case as squares. So when you're trying to compute the distance from that pixels to that pixel, in reality what you're doing, you're actually computing the distance between its left top corner, because that's the coordinate of this of the pixel, to the left top corner of another pixel. So that's the distance you're computing. That's why the entire image is sort of like shifted to the left top corner, right? So it sort of like goes in here, right? Because you're computing the coordinates like that. What you have to do, you have to start doing subpixel computations, and you start to compute distances between the centers of these things, and that way you can get rid of these sort of artifacts. So at some point, since we're going to be doing like a physics simulations, we're gonna switch to floating point coordinates anyway. So, and the subpixel computations will arise naturally. All right, so that's why I don't really worry about this right now. So what I do worry about is the fact that the circle looks like shit. That's what I care about. Look how tall it is. Like it doesn't look like a circle, it's an ellipse. The fuck? It doesn't look good at all. So like, this is bullshit. Like, how are we supposed to make it bounce? It's like it's like an American handball thingy. You know what I'm talking about? So, and this is because the height of a character is bigger than the width of the character. So we cannot treat pixels when we do ASCII graphics as square. They're rectangular one. So we can try to do something about that. We can try to treat each individual character as actually two characters, or as two pixels, right? Let me sip my tea and we can try to tackle that. So basically we need to somehow like compress this entire thing a little bit and make it look better, because this is no bueno. This is no bueno 100%. All right, so let me see. So here's the ball scene. So where is the show? Here is the show. So essentially, if we have some sort of stuff in here, so we're gonna be having so something like this. And we're gonna have several rows of these things. I actually want to make them slightly different. So right, and we can sort of copy paste some of these things like that. Yeah, there we go. So imagine that this is the state of the display, right? This is the state of the display. And to compress the entire thing, we need to treat pairs of rows as a single row, right? So we need to basically render everything not by one row, but by two rows. How can we compress two rows of characters into a single row of characters? Well, in a row, we have two situations, right? When essentially you have two empty pixels, right? Two full pixels, and two situations when first one is empty, the second one is full, and do we have an opposite situation? Yeah, and another situation is when this one is empty and this one is full. So we have four situations. So for each individual four situation, we're gonna construct a new row can I actually have something like that points down? So Unicode arrow point down. So I just want to have that. For a better visual representation. There we go. So because it's a single character, so maybe... it's wide. It's too freaking wide. Anyway, so that means I probably have to do something like this. There we go. So we're gonna compress this into a different character. So a character, we need to have a character that at the bottom of its glyph has more stuff than at the top, if you know what I'm talking about, right? So I don't know, maybe something like underscore. Right, underscore is a pretty good candidate, right? It has right, more things at the bottom than at the top, and it looks like 2 pixels with the bottom pixel being full and the top pixel being empty. Okay, so it's ASCII art, what can I say? And this one is also going to be something like this. Now we have the second situation, right? It's when the top one is full and the bottom one is not full, is empty, right? So, and in that situation, which sort of character like corresponds to that? I'm not even sure. So maybe carrot? Is that how it's called? Like it's a carrot symbol. I keep forgetting how carrot and not carrot. I'm hungry, okay? So the circumflex symbol, okay, that actually sounds pretty fancy. I would like to use that name except instead of carrot. Circumflex, ampersand. Nice, really like that. Okay, so, and as you can see, we have a bunch of these kind of situations. I can probably fill that in as an indication to what we're actually converting things. So, you know, maybe we don't need these arrows anymore. It's kind of like obvious what I'm trying to say in here. So here's another one. And now we have a situation when 2 characters as empty. Well, that is easy. That is straight up space. And here we have another space. And here we have another bottom one. And okay, we need to come up with a full one, right? So what's going to be the full one? We need like a tall character that looks like 2 filled pixels. We can use something like at. Yeah, that seems to be right. But to be fair, at is too thick, right? So it would be nice if we have a character that has like a thin line at the bottom and thin line at the top. To like sort of match the look and feel of underscore and the circumflex symbol. Really like this name. It sounds so fancy. Maybe it's a little bit of a stretch, but how about C? You know, so it kind of has like a thin thing at the top and thin thing at the bottom. Right, and it kind of looks like both the circumflex and underscore together, but with a line between them. So it might work. It kind of might work. So yeah. So, and here we have that. So essentially, we are translating these 2 rows into this single row, effectively compressing it and sort of trying to fix the ratio. Right, and we do that for each individual line in here. So, so maybe we can indicate. So this one is going to be bottom, bottom. Might as well actually flip them around. So this is going to be top, top, bottom, bottom, space, space, top, C, 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 space, space, space. There we go. So that's how these lines will look like after the transformation of our nation. Oh. I'm really sorry. Anyways, so because of that, here's an interesting thing. The display will not contain the final pixels anymore, right? So initially I wanted that the display is going to contain the final pixels. You just place these final pixels into the display and you're good to go. But no, before rendering them, we now need to compress them by 2 rows, right? So, and I suppose we could basically now introduce something else in here, right? So we can now say we can have a pixel, right? So this is abstraction and we have pixels now. And let's introduce enumeration, right? So this is going to be pixel. And what kind of pixels are we going to have? So we need to have like a full and empty, right? So full and empty. Empty, full. And I don't really like this thing because empty is longer than full. So it's just like, it bothers me. Because I have an OCD. There's no particular reason, but I have a pretty bad OCD sometimes, and it just like bothers me so much. So maybe we can do one thing. Empt, full. Yes, kawaii freaking desu. So it's empty. You know what? It's a pixel. It's a color. It's a background and foreground. Back, front. Back, for. Yeah. Background, foreground. Looks good to me. And the background is going to be 0 and foreground is going to be 1. So, and this is quite important, right? Because then we're going to be using these things as an index in a table of the pixel substitutions, right? So we're going to have a table of the pixel substitutions. So it's actually not quite clear that these are the spaces. I wish it was a little bit more clear, but I don't know how to make it more clear. Maybe I could show the boundaries of these things. Maybe, I don't know. And then we can have a single thing indicating how it gets transformed. Right, so we can have something like this, and yep, okay. I'm not sure if the second one is that important. It's a double row pixel compression. Double row pixel compression. Cool. So that means now we have a bunch of displays, and when I fill something, I actually fill the pixel, right? So something like this. So it's filled with the pixels, which does not necessarily make any sense because memset fills everything by byte, anyway. So let me see. Memset fill memory with a constant byte, but the size of the pixel might not necessarily be byte. So what we have to do instead, I suppose, is probably finally iterate this entire thing. We can organize like a very simple loop, I suppose. Right, so we can have a pixel pointer and size tn. So the initial pointer is going to be display, right, and the size is going to be width multiplied by height, right, and then we can organize the old school, very old school C loop where we do something like this, right, and then we dereference the pointer, but before we dereference the pointer, we're going to be incrementing it and then setting the pixel that we want to set. There we go. Very old school way of filling up the array. I hope I didn't do any buffer overflows, right? So essentially, this is like, you know, it scares away a lot of new C developers. But essentially, the precedence of ++ is higher than the precedence of the dereferencing. So that's why ++ will happen first. So what this thing does, it increments the pointer by one element, right? So it jumps to the next element. But since it's a post increment, the entire expression returns the previous value, the previous element, and then dereferences the previous value. So that way we are essentially referring to the current pixel and incrementing to the next pixel simultaneously within 6 characters, right? So these 6 characters simultaneously increment the pointer and refer to the current pointer before the incrementing, and we just set this to this thing, and then we keep tracking how many things we already set, so we don't buffer overflow. So that's basically what it's all about. Pretty straightforward, and you can find this kind of stuff in old and also low level C code quite often. So it's a quite common thing to do this kind of stuff. So, and that way we setting things not by bytes, but already by pixels, because pixel can be bigger than a single byte. I think in this case it's going to be integer, so I think it's going to be 4 bytes, but it's 2021, memory is cheap, so it's totally okay. It's totally okay. Don't worry about that. So I guess that's everything I wanted to do, maybe, in this part. So let's try to implement the show now. Quite important thing. We will now iterate the display not by rows but by pairs of rows, right? And to simplify ourselves life, we're gonna demand that the height is divisible by 2, right? I don't want to mess with the case when it's not divisible by 2, right? So let's just demand that the height is divisible by 2. So if it's equals 0, right? If the amount of display rows is not divisible by 2, we can't properly compress it and can't properly compress it. See show function. Okay, wait, there we go. So, and for static assert, I think we also need to include assert, otherwise it just doesn't really work properly. So what we're going to be doing here, again, we're iterating by pairs of rows. So that means we have to do something like divided by 2. So now y points at the pair of the rows, right? It points at the pairs of the rows. So, and I suppose what we're going to be doing, we're going to be collecting like a row of characters to display on each individual pair of rows, right? So we're going to have a single row of characters of the size of width, right? And I'm allocating it on the stack, and it's totally fine because width is actually very small. But in case somebody will make it big, we may want to actually put it in a static, right? So it's basically visible only within the function, but it's located outside of the stack in a static memory. All right, so, and essentially now, we are iterating by pairs of rows, right? So here's the first pair. And we need to iterate each individual sort of column of that row, right? Each individual pair, and compress it into a single character, right? So let's quickly do that. We need to do x0, x less than width, plus x. All right, so the first pixel, so we're currently looking at, let's say, this pixel, right? Whatever. We need to get the value of that pixel, right? So this is going to be the top pixel, the top pixel. The top pixel is located within the display y multiplied by 2, y multiplied by 2 because it's a pair of rows. Multiplied by width, which is the size of a single row. And do we have to do plus x? I think we have to do plus x. There we go. So, and we are doing plus x. So this is the first pixel, if I understand correctly. So the bottom pixel, the second one, is going to be located on the second row, right? So that means we have to do plus 1 for the second row. So essentially here we have like invisible and implicit plus 0. So this is the row 0 and row 1. It's offset within the row. And that's how we get the top and the bottom pixel. So if the top pixel, or if any of the pixels are empty, their value is going to be 0. And if they're, well, they're not empty, the background. If they're background, they're going to be 0. If they're foreground, they're going to be 1. So that means we can use these things as indices within two-dimensional table to actually find and compress the corresponding character, right? So let's actually define such table somewhere here. So this is going to be a table and it's two-dimensional, right? So we have two amount of pixels, going to be 2 by 2. So we have an idea actually. We can apply the usual trick, basically count pixels, right? So this is how many colors we have essentially, right? So how many pixels we have. And the table is going to be basically count pixels, right? Not really sure if it was worth it, to be fair. It's probably not worth it. I mean, it's such a simple application, it's probably not gonna really grow too much into the future. And if it will, it's not that difficult to notice that and fix everything properly. So let's just hardcode that, it doesn't matter. So the first row, I suppose, is gonna be referring to the top, right? So if I do something like this, the first index is going to be the top, and the second index is going to be the bottom, right? So that means this is basically when the top is 0, and this is when the top is 1, right? So this is the top. Okay, and now we have a situation. So the top is 0, and the bottom is 0. The top is 0 and the bottom is 0, so that means it has to be space, right? And if the top is 0 but the bottom is 1, it has to be underscore, if I understand everything correctly. There we go. All right, if so so how can I indicate all of that? So maybe we can even do something like this. So if the top is 1, but the bottom is 0, that means it's a circumflex. And if both of them are 1, that means it's C, right? And in here we have a situation, right, something like B. I'm just thinking, what's the easiest way to actually sort of display all of this, right? So it could be something like this, right? Like this, and then we can remove T, right? And this one is going to be something like T. There we go. So basically this is bottom and this is top, right? So yeah, roughly like that. So bottom and top are 0, this is space, top is 0 but bottom is 1, that means it's that, and there we go. So we have a table. So now what we can do, essentially, we can look up everything in that table, right, like this, and shove it into the row, right? So, and the row is indexed by X, right? There we go. So we filled up the first row. So, and the next thing we can now do, we can write that row into the display, right? So this is going to be the row. The size of that row is going to be the width. The amount of row is going to be 1, and we're going to print on all of that with the standard output. And after that, we can just put a new character in here. So this is going to be new line std out. So that's basically how roughly we can compress this entire thing, I think. I hope I didn't do any forky-walky and potentially oopsie-doopsie. There we go, and I did! Yay! But it kind of looks strange, not gonna lie. Well, this is because Emacs actually displays it like that. And it's because Emacs displays it like that. Oh, this is because... Okay, that's... Alright. So, it basically silently converted character into a pixel. We can actually do something interesting, I suppose. So do we have a count? So this is, okay, this is the second time I need to know the amount of pixels, right? So this is the second time. So maybe it makes sense to introduce count pixel. But I don't like it, it's such a long name. Let's actually call it pixel n. Yeah, let's go pixel n. And in here, essentially, I can put pixel n. So this one is going to be pixel n, and at least in runtime now we can assert that t right is, you know, less than pixel n, right, and b also is less than pixel n. Ideally it would be nice to also assert that it's greater or equal than 0, just in case. Well, let's do that. So all of these assertions will probably fail, right? But at least it will help us to catch these kind of situations at runtime. Catching errors that should have been caught at compile time, at runtime, in a statically compiled language. God damn it. Like, why are we still messing with this language? My God. Anyway, so yeah, we call that thing, and I'm basically filling up everything with the background. So that still doesn't solve the problem because we also have to use the background, and I think I even like use all of the necessary flags and shit like that. It's just insane. There we go. Now we're talking. Now we can't see shit. I'm so happy. Right. So the question is why. The question is why. The question is why. Didn't feel anything when it was actually like sending garbage. It was kind of fine, but now it is like it doesn't really work anymore. So that is very, very strange. That is very, very strange. So why would it be like that? I wonder. So I have a feeling that we need to bust out the debugger and just look at all of that in the debugger. I think that's the thing we need to do. So do I even enable any like debugging information for the ball? I think it makes sense to actually enable that just in case. And let's take a look in the debugger what's going on. So this is going to be ball, and I'm going to break at, I suppose I want to break at show, right? So let's break at show and let's run this entire thing and let's take a look at what we have. Maybe I'm going to take a look at the display. Back repeats 124 times. Huh. Is it? This is very strange. It didn't feel anything. So already in the debugger, we can clearly see that circle didn't do shit. Right, so everything is still back. Everything, oh, because I explicitly said back, okay. I think I need to make a small break. Yeah. Now we're talking, look at that. Oh shit, that looks good. Fuck. And it looks round. Well, I mean, it's still a little bit like tall, but it's less tall than it was before. God dang, look at that sub-pixel ASCII graphics. No, that's a sexy circle, my god. Anyway, so we can try to play with the radius stuff, I suppose. We can make it like twice as small now. Yeah, now here's the circle. I don't know. How about that? How about that? Isn't that amazing? I think it's goddamn freaking amazing. So one of the things I want to do now is probably animate that circle, right? So, but let's do that after a small break because I need to refill my cup of tea and, you know, the usual stuff. So let's go ahead and, all right. So let's try to animate this circle, okay? So here we have a center, but in reality it's a position, right? So we keep track of the position. Let's also introduce maybe the velocity, right? So it's going to be vector I, velocity, and let's say that it's going to be something like, ooh, maybe it's always going to go down, right? So x is not going to change, right? X is not changing, and in terms of y, we're going to be increasing by a particular value. The value I don't think matters that much, so I think it's going to be just 1, right? So, and let's try to simulate like a couple of frames of this animation, right? So let's say that we're going to have 10 frames of this specific animation. So we fill the buffer, then we render the circle, and then we show that specific frame. So maybe it would also make sense to separate everything by some sort of a line so we can see between the frames. And every time we're rendering, we also need to update the position. The position is basically vector I sum, right? Vector I sum position plus velocity, nothing particularly special, right? So let's try to do that. And there we go. So we have a ball that is sort of, yeah, it is going down. So maybe we can actually increase the velocity by 2 because it's actually going very slowly. You can see the subpixel. So here's the next frame, and it didn't really change much, I think. I don't know, it actually doesn't really change. Okay, oh, yeah. So the subpixel stuff was visible when we were moving by 1 pixel. Yeah, you could see that there is no C in here, and now C appears. This is because a single character is not a single pixel, it's actually 2 pixels, right? So that's why it looks like that. Yeah, that's pretty cool. and it just goes down, and it will continue going down as we render more frames, and so on and so forth. Yeah, so we render more frames. Okay, so, but this is actually kind of lame, to be fair. I want this thing to be more or less interactive. Not really interactive, but I mean, I want it to be an animation, in a sense like N-cursors can play animations. But at the same time, I don't want to depend on N-cursors, and I don't think we have to depend on it. So there is a trick to use specific ANSI terminal codes to sort of, when you render the frame, right, the cursor actually stays at the right bottom corner of your frame. And using ANSI escape codes for your terminal, you can actually bring it back to the left top corner where it started and try to render again. Then you can bring the cursor back and try to render again, and so on and so forth, creating an effect of the animation without any incursors. It's actually escape codes for this kind of stuff are simple. I already did this kind of trick before, but I don't remember where, so we'll have to reinvent this shit from scratch again. So I wish I could copy paste the code that I did a long time ago from somewhere, but I don't remember where I did that. So we'll have to do that from scratch. It is what it is, and it isn't what it isn't. So anyway, we need to probably organize like an infinite rendering loop, right? For that, we're gonna have a quit thingy. So by default, it's 0, and while we're not quitting, we're going to be rendering everything. So here is the thing. If we're going to be rendering everything in a very naive way, I don't think it's going to work really well. Maybe it will. Maybe it could go actually well. Yeah. So if I go back to like the corner, right? If I go back to the corner, we're kind of like missing the first frame if we're doing that. Right, you see, so we're missing the frame where initial state is computed. Yeah, because we first updating everything, right? We're updating everything, then we're rendering the entire thing, and then we're going back to the corner, right? We're going back to the corner. So if we want to render the first state, right, we have to do it in here. Right, we'll have to do that in here. Then we'll have to compute the next state. Right, we'll have to compute the next state. And where do we go back? Maybe we, you know, we're gonna just miss the single frame. I think it's gonna be the easiest thing to do. Like, who cares? Like, we have like playing a lot of frames. Like, who cares if we miss the first ever frame? Like, is it that important? I don't think it's that important. Let's just miss it. Right, it's gonna make the entire thing like a little bit easier for us. Okay, so how can we do a back thingy? So let's actually do something like avoid back. So in that function, we have to just go back to the top left corner somehow. So ANSI terminal escape codes. I don't remember how to use them. So Wikipedia, build your own command line with ANSI escape codes. Okay. Cursor navigation, that's what we need. That's what we need in here. So up and down. Ooh. It's a Python thingy. Okay, so this is 0, 0. I suppose it's a 1B. And what is 1B? It's a 27. And I think 27 is exactly escape. I think it is. If we take a look at this stuff, it is in fact escape. So it is escape sequence. I think that's precisely what we need in here. So that means I'm going to actually put this entire thing in the description as a reference. Right. Website I stole the ANSI code from. I wish there was like some sort of documentation, like in man pages, like man ASCII. Right, so where I could look up this kind of stuff. Is there something like man ANSI? No, I don't know what that is. So maybe there is something. ANSI terminal escape codes man page, manual page, console codes. There is something like that. Holy shit! So cursor movement. It may trigger cursor movement. Okay, so let's just search for cursor. Do I even have that on my local machine though? Wait. That is it, I think. This is completely unreadable. I don't know how to interpret this thing. Yay, that's cool. Do I have that local on my machine? Let's actually see. I do have that. Oh my god. I'm so happy. This is absolutely unreadable. Cool. I'm gonna use this website. All right. So we need to move left and up. Right. So this is what we'll need in here. So let's first move left. Where's the ball? Here it is. So essentially, if I remember correctly how to do this kind of stuff, right? So I have to do escape code. I don't quite remember. Can I just escape C escape escape code? Escape sequences in C. If I remember correctly, okay, so we have that byte whose numerical value is given by n, interpreted as octal, and this one is interpreted as hex. Okay, so I can have hex in here, so this is basically what I need to do in here. So I think, yeah. So, and I don't think we need leading zeros in this particular case, do we? The byte whose numerical value is interpreted as a hexadecimal. Okay, so let's actually ignore the leading things in here. So this will be 1b. So then I suppose we keep this thing around, and then this is where we put the amount of steps we want to move to the left. And the amount of steps we want to move to the left is going to be the width, right? So that's basically what we're doing here, I think, if I'm not mistaken. Right, so, and the other thing that we need to do in here is up. It's very much similar, right? And I think the only difference is that it's basically A instead of D, right? So, and up we move height amount of times. Cool. So yes. So a single frame is essentially cleaning up the buffer, right? The back buffer, rendering a circle, showing this entire thing, and going back to re-render it, right? So this is a single frame, like 4 function calls. If we did everything correctly, hopefully, we'll see. So let's actually recompile the entire thing, but I don't want to run it inside of Emacs because Emacs is a very slow terminal. Okay, so we have, this is not S, it has to be D. Yesu, and if I try to run the ball, it did a thing, but I'm not sure what the hell has happened. Okay, that is very, oh, I think I know what is going on. So we actually render less rows than we're trying to move, right? Because we compress the pairs of rows into a single row. So that means we have to actually move height divided by 2. Let's see if it's gonna work. Okay, it did a thing, but I think it was too fast. It kind of renders correctly, but it's doing shit too fast. Let's actually sleep a little bit. Okay, so I think we can use usleep. And usleep is in nanosecond. No, it's a microseconds. Okay, so if it's a microseconds, right, a microsecond, 1000 is a millisecond, and this one is microsecond, and we need to divide it by FPS. Let's actually define FPS as the constant in here, right? I think it's going to be useful. Define FPS is going to be 60, right? And that's how much we sleep. Hopefully now this entire thing is going to be visible. Usleep, we need to include unistd, right, for this thing to work. And I think you also need to define some sort of like a macro thingy. X open source, I think, if I'm not mistaken, before X open source. Okay, so we can say that this is a X open source code, whatever that's supposed to mean. I have no idea, but every time I include one of these macros, my code starts to magically compile. So that's basically what I'm doing in here, and it didn't magically compile, unfortunately. So, oh, you have to define specific values. So 500 Is it gonna, now it works. So I suppose you basically indicate what kind of standard you're using, what kind of version of standard, and so on and so forth. There's shit ton of standards like POSIX, SAS, and whatever the hell these things are. It's a mess. I don't understand it. So I just stick this macros until my code compiles, and then I'm happy. All right, so we're trying to slow it down. Maybe 60 FPS is too fast still because we're on a terminal. Let's actually do something like 15 just in case. Right, let's just do something like 15. Let's just, oh, holy shit! The fuck? Oh wow, that's cool. That is cool. We have a ball that moving around. The fuck? The fuck is this shit? Oh my, that is so cool. Look at that ball. Look at it go. Look at that go. Nice. I can't stop looking at it. It's so nice. Let's actually make it move since the top. All right, so we're gonna start at 0, but 0 is essentially yeah, let's actually remove this thing. Maybe we can simplify the entire thing. But the 0, it starts at the center of the circle, right? So what's the radius? Okay, so let's actually define the radius somewhere here. So this one is going to be a radius, and this is basically width divided by 4. And we're going to start from the radius of the circle, right? And this one is going to be the radius, right? So it's going to basically scale with the width of the screen, right? So that's going to be basically the idea. And if I try to run it, so it starts from the very, very top, right? Even though we're kind of missing a single frame, but that's totally fine. So that is in fact totally fine. So now we want to sort of like play, like simulate physics and whatnot, right? Okay. To simulate physics, we probably need to switch to floating point computations, right? So let's quickly do that, I suppose. I suppose I'm gonna start by just replacing these things with F and these things with F as well. So we're gonna start with the half of the width, and because it's a floating point, I'm gonna be using floating point literals. So, and the radius will also become a floating point now. There we go. So everything is a floating point. The velocity, I don't know. I think the initial velocity has to be 0, right? So because we start with the velocity 0. And then we're going to be modifying the velocity according to the gravity, right? So we also will need to define something like gravity. Snap back to reality. So let's say the gravity is going to be like around 100, right? We can adjust that later. Okay, so how the simulation is going to go now? First thing we update the velocity. Right, so we're going to do v to f sum, right? We do sum velocity plus gravity. The gravity is actually rather interesting. So we have to point the gravity like down. So maybe we want to have a special vector in here. So gravity, so v to f. So gravity doesn't affect the horizontal thing, so it's going to be 0, but it does in fact affect the vertical one. So that means it's going to be just gravity like this. So there we go. And essentially we're adding this gravity, but we also need to scale it according to the time, right? Because we're running with 15 FPS. So we need to have a delta time in seconds. So let's introduce such delta time. I think we can have a fixed delta time. So essentially what we need to have here, we need to, let's call it dt. And it's going to be 1 over FPS, right? So this is going to be 1 over FPS, and there we go. So, and in here I'm going to take the gravity, v to f multiply gravity by essentially v to f dt, right? v to f dt. So I scale gravity by the delta time, and then I add it to the velocity, and here you go, here is the new velocity. So once we updated the velocity, right? Once we updated the velocity, we use that velocity to update the position, and the velocity also has to be scaled according to the delta time, right? So everything is scaled according to the delta time. So it's a physics dependent on the FPS. So that's why it will be tunneling and all sorts of things, but this is a very simple thing, so we don't care. All right, so this entire thing will now accelerate. Even though its initial velocity is 0, it's because of the gravity, it's going to be constantly accelerating down. All right. So let's take a look at what we have in here. So we have a couple of compilation errors. So this one has to be FF, of course. So what else do we have? Oh, circle. Okay. So remember how I said that we're going to slowly evolve that into floating points? So I think the time has come. Let's actually replace all of that with floating points. Right, so this is going to be something like this. To be fair, I still want to keep begin and end integers because these are the actual characters that we're going to be iterating, right? So these are the actual characters. So I suppose center and this thing are going to be floats. Oh my god. Emacs, everything. So, and yeah. We basically calculate the boundaries in floating points. The next thing I want to do, I want to take the top left boundary and actually floor it, right? In case if we have any fractions or anything like that. So I'm going to use v to f floor. And the right bottom boundary, I want to actually seal it, right? So basically it will sort of like snap them to the corresponding pixels and whatnot. And after that, I want to convert the floating point vector into the integer vector. So that means I'm saying I'm constructing integer vector to two-dimensional integer vector from the two-dimensional floating vector. So that's how you can do that. Yeah, there we go. So basically, the library follows the conventions, the naming conventions, and according to these naming conventions, to construct integer two-dimensional vector from the float two-dimensional vector, you have to, use this kind of constructor. You can even take a look at how it's implemented in the library itself. Let's actually see. Here is the constructor, and in fact, what it does, it accepts the two-dimensional floating point, returns the integer one, and what it just basically explicitly converts everything for you. So yeah. There we go. Looks a little bit noisy, to be fair. But anyway, so what do we have in here? So this is the distance. This is the distance. And I suppose what we're gonna do with all that stuff. So cx and cy are floats and x and y are integers. And this is where it kind of gets messy. So I think the final thing has to be float, right? It definitely has to be float. So, but here, x and y points at the left top corner. So yeah, so we have a similar situation here, right? We have a similar situation. So here is the center, but x and y, they point at these corners of the pixels. They point at these corners of the pixels. To compute the actual distances, we have to take that corner of the pixel and sort of add half of the pixels, so we're computing the actual distances between these things, right? So that means here, when we're subtracting, we actually want to subtract not x, but plus half, and we want to make sure that this thing is a float, right? We want to make sure that this thing is a float. Something like this. And we're already doing vector arithmetics in here. I think we can compress these two lines into a single one. We could have something like, I suppose, vec2fd, where we take c, right, and we subtract vec2f, subtract. And what do we need to subtract in here? We need to subtract the x and y vector. So to do that, we have to construct such vector, x and y. But we can actually construct it like this. We can like explicitly make them floats, right? Right, we can explicitly make them floats, and maybe we still can split that into two lines. Yeah, we kind of still splitting all of that into two lines. Vec2f, this is going to be the position, right? So this is the position, and essentially we're doing vec2f sum, vec2ff half, right? There we go. So that's the thing, and then we take the distance between these two things. Maybe we can go even like more bananas and just construct an integer thing in here, right? And then convert the integer thing into the float thing, right? So this is the integer thing, then we convert it into float thing, and to the float thing we add half of the pixels to find the actual center, and then we compute the distances between those two things. And maybe you can even inline this entire stuff into there, but I don't know if it will make the readability worse, right? So we'll see. Anyway, so after that we're kind of calculating, that's very interesting actually, we're calculating a square length of the vector d, right? So in here we have vector f sqr len, and that's literally what it is, right? That's literally what it is. We can basically replace this with f2f sqr len of d, and there you go, right? So that's basically it. So we made sure that everything's okay, and if x and y are within the boundaries, we actually display everything accordingly. Okay, so we migrated the circle into floating points now. Cool. Can we compile this thing now? I wonder. Okay, undefined reference to florf. Oh, okay, that's very interesting. So it means we need to actually link with the mathematical library. So we're starting to use the mathematical library now. We were not using it before, but now we're using it. Okay. Oh, right. So it starts at 0, and then, as you can see, it basically accelerates. Okay, that's pretty cool. And floating point stuff still works. I'm super happy about that. So what's going to be the next thing? We can try to do something when we hit the floor, if you know what I'm talking about. So when do we hit the floor? It's when the y position becomes bigger than the height minus the radius of this thing. So in that case, we are hitting the floor. We are hitting the floor. What do we have to do in this particular situation? Well, we can basically invert the y coordinate of the velocity to make it go upwards, so it will sort of bounce off of the floor. So yeah, we can try to do that. So we can take the velocity of y and multiply it by -1, and maybe that will make it bounce. We'll see. And boom. All right, that's funny. Okay. I suppose, yeah, maybe we also have to reset the position all the time. So if you hit this floor, right, if the, yeah, so let's actually make it equal always, right? So let's keep it equal always. And, oh, okay, so it keeps bouncing. Not bad. So it's almost what I wanted to have in the first place. We're almost there, essentially. We're almost there. But I think I wanted to actually stop at some point, right? Let's actually make it stop at some point. So to do that, we have to actually multiply it not by 1, but something that is less than 1, right? So every time you hit the floor, you sort of lose a little bit of energy, a little bit of a velocity. So let's actually do something like 95. So over time, you're going to be losing the energy and the velocity. So maybe 95 is too small. But as you can see, it's just like sort of slows down. We can make it like 80 or something. Not bad, and then it actually stabilizes, right? And since we always have this condition, right? We always have this condition. It will never go and through the thing, so it's always going to stay here. It's pretty cool. So what if we can actually turn it into some sort of constant? Let's actually call it something like damper, right? And we're going to define it like this. There we go. So maybe we want to make the gravity a little bit more harsh. So what's going to be that? Maybe not that harsh. Not bad. So maybe we could increase the resolution. How about height being 64 and width also being 64? Is that a good resolution? So That's not bad. Maybe a little bit too big, but it's actually looking pretty good. All right, so let's actually keep it 32. So width is gonna be, what if we keep height 32? Yeah. Oh yeah, it's too small. Oh, I know why. The radius actually depends on the width. Let's actually make it depend on the height. Maybe it should be like a minimum between these two. Okay, that's not bad. Okay, so I want the application to exit when the entire system sort of stabilizes, right? So I don't want it to play like indefinitely. I want it to finish at some point. So I don't really know what could be a criteria of this system stabilizing. So maybe we could make it go outside of the screen. Okay, so what if we give it initial velocity of like 100 to the right? So this one becomes f. All right. wait. So what if I make it a little bit smaller? Okay, what if we start, in fact, at radius, and effectively this becomes this. All right, so... okay, and this could be actually a criteria. So when the... this actually looks good, I really like that. This is just like, yeah, I'm rolling, I'm out of here. I'm fucking out of here. So essentially when it's basically to the right, while... maybe we can even get rid of the quit, but quit is not needed anymore. Position X is greater than the width minus the radius. I think this is how we want to do that. So, and I want the application to quit. Okay, so it's the other way around. Plus the radius. My brain cannot visualize that for some reason. Really? Okay, so I need to visualize that. Okay, just give me a second. So let me check that I understand. Okay, all right. So yeah. Here is the position and here is the thing. So you want to check while X is less than width plus the radius, because that's basically what it is. It's the width and the radius, right? And you're trying to check if this thing is less than that stuff, right? While position X is less than width plus the radius. That's the criteria that we want to have in here. So while this thing is less, we keep playing animation. If I understand everything correctly, my brain... and then it stops. Perfect. Actually, that's actually super cool. We can even probably add a little bit of like a padding in here. So maybe... this is not here. Plus maybe half of the radius, a little bit, just so it has a little bit of time before exiting. Right, so... this looks cool, I really like that. Is it gonna fit into, you know, usual terminal? I think it's gonna fit into the majority of the terminals, yeah. Yep. That's it, I suppose. That could be the demo of the library, which is actually kind of cool. So, yep. Let's clean that up a little bit. Do we even need to clean anything up? I don't really know. Oh, I have an idea. I've got a pretty cool job security idea. So, look. That's pretty cool. So, the characters in memory are located like this anyway, right? Space underscore circumflex NC, right? So, and basically we can construct an index out of these two things and get rid of this table completely. So it's going to become even more unreadable for the people who never watch this video. Yes, that's going to be our little secret. We're going to write the code, follow all of the logical steps to understand how we came to that code, and we're going to make it unreadable unless you actually went through the same steps, right? So this way we're going to force people to watch the videos. No, we're not going to do that. If people don't want to watch the video, they're not going to watch it. But I want to do that anyway. So essentially, we basically use the same memory layout. This thing is laid out in the memory the same way as the string. So, and that may actually simplify a lot of stuff. And essentially, you can just put this thing like that. So t multiplied by 2 plus b. There we go. So that's the whole thing. And you can get rid of this weird ugly table, and let's see if it compiles, if it works. Yeah, there we go. So that was easy. So that was easy peasy lemon squeezy. So we can remove this entire thing, and we can even make this stuff even more unreadable. So multiply by 2 is basically shift by 1 to the right, and in that case plus is going to be just OR for the b. So this becomes even more unreadable. Right, we're basically constructing an index out of the bits of the pixel, right? And that's basically what it is. What it is. It is what it is, and it isn't what it isn't. We also have a couple of assertions in here. I'm not sure if it's a good idea generally. I don't know. So yeah, so now a show function is actually super simple. It is in fact super simple. Maybe we can get rid of these assertions, to be fair. I don't know. Because we're probably not going to have more than 2 colors anyway. Whatever. Whatever. So, yep. I guess that's it for today. This is what we've got so far. I have a pretty cool idea. I can do something like while 1, right? So this is going to be while 1, and as soon as you hit this condition, right? As soon as you hit this condition, we're going to be resetting the whole system, and resetting the whole system is effectively just doing that, right? So I'm going to be doing 13, right? So this one is going to be like this. There we go. So it would be nice to have like a special function to do that, but it's just an example, so it doesn't really matter. So, so it has to be the other way around, not. Yeah. You know what, it would be even cooler if we actually start completely outside of the screen, meaning that minus radius. Does it really start? Oh yeah, we restarted incorrectly, so we also have to do that in the restart. To do that, I don't know, so maybe we could make these two things global variables, right? And then reset, and reset effectively does that, right? And every time you have this kind of situation, you do reset, and then before starting you also do the reset. So that way, if I modify any of the parameters in here, it doesn't really matter. Right, so and this entire stuff is just, you know, this stuff. Static. So this is a small example, so because of that, the global variables are fine. Trust me, I'm a professional software developer. As a professional software developer, I am telling you, global variables are fine. Trust me. So in here, we could probably actually get rid of the multiplication if we do something like dt, right? So that way we can just do something like this. There we go. So that becomes even simpler. Yep. Let me see. So boom. We can add a little bit of more padding, right? So it could be like 1, So maybe the padding has to be like a special constant here as well. What about 2 radii? So the bigger the padding, the more time between the balls will pass. I like this, actually. Oh, I have another idea. What if we increase FPS? So what about 30 FPS? I mean, surely modern computers can do that. Holy shit, what the fuck? Wait. I can render at 30 FPS on a console? The fuck? I didn't know that. So I think I don't like how it doesn't damper properly. So I want actually this thing to damper even more. Let's put 65 in here. Yeah, it's a little bit better. So it dampers a little bit more now. Yeah. How about 60 FPS? Can we do 60 FPS in here? I'm not sure if 60 FPS makes any difference, but it looks fine, I guess. I don't know. We can keep it 30. Let's keep it 30 to make it console friendly. Alright, so that's pretty pog. So I guess that's it for today. Thanks everyone who's watching right now. I really appreciate it. Have a good one, and I see you all next time. By the time this video will become public, the code should be available in the repo. So I'm not gonna push it right away to avoid any spoilers of this entire thing, but it should be available here, and it's gonna be the demo that demonstrates you how to use this library. As we already learned, this library is absolutely horrible. What the fuck is this shit? But I mean, if you kind of get used to that, it makes sense. But at least I'm the one who's going to be using this library, so I'm primarily making this library for myself, and it works fine for me. I guess I managed to make a small ball animation thingy, so which simulates the physics and shit. That's pretty cool. That's pretty cool. All right, thanks everyone for watching. Hope it was interesting, and yeah, love you all. Mwah.